I really hope that you can participate, because as I say, in this class, I want to have an atmosphere to immerse you in all the terminology. Every slide looks complicated, but if we keep talking about this, repeating, I hope that you understand by your heart. Right? That is the purpose of this class. And I want to teach you some trick and some hand-waving methodology, but which is correct, not hand-wavingly wrong, right? I hope that I can teach you that, because all we are going to learn can consume a few semesters if you want to learn it really deep, right? So that's why your participation is very important. If you just think that you join this meeting and not listening, and later just run through the slide with 1.25x, this won't be good for you, okay? Now, so let's look at the capacitor. We already draw the band diagram. I repeat it on the top right, okay? So what if I apply a gate bias? So another thing I am trying to repeat, right? I'm sure many students taken device physics, they don't understand this, they forget about this. They mess up the difference between Fermi level and the band bending, right? So as I said, when you apply zero bias, Fermi level has to be constant when you apply zero bias, right? This is zero bias, 0 volt, right? So you give a constant Fermi level everywhere in your system. That's the meaning of zero bias. But your structure may be bending, okay? So it doesn't mean that there's no bending. In this particular case, as I said in the last class, it's just a coincidence that it is not bending, okay? Now, what if I apply a negative bias? How would the structure look like? I give you half minutes, very quickly. Can you draw on your paper? When I apply a negative bias to the gate metal, how would the band look like? Right? This is just to test how yeah.
It will push up the Fermi level. Will push
where?
up.
Where?
It will bend it. It will bend it towards the conducting band.
Hold on. You just say that it push up the Fermi level. Which region? Which region? On the metal or on the semiconductor?
On the semiconductor, not on the metal.
Can you think carefully?
You said an input positive bias, right?
Oh, did I say positive? I want negative gate voltage.
Oh, it will bend it down. Then it will push it. It will push it down. The Fermi level on the semiconductor.
Okay, good. So you are right, but I don't think it this way. You try to say it push down the one in semiconductor, right? I will try to say it push up the one in the metal. So you are right. It just we saying different thing, right? Now, but now I try to instill. I force you to think in my way. You don't have to, like the student who just said, right? He get the answer correctly already. He doesn't have to follow my approach. If you don't, then follow my approach. I just tell you the answer first. When Vg smaller than 0, okay, this is Vg. You will see something like this. This is the Fermi level in the metal. This is the Fermi level in the semiconductor. This is exactly the same what he just said. It pushed down the Fermi level in the semiconductor. But I try to look at as push up the Fermi level in the metal, because I try to look at applying a negative bias to it. So when it is push up, then there will be some band bending, right? Think about this as some rock, right? Or some rock, they are connected by some joint, right? If you push up this part, then this is going to bend, right? Correct? And similarly, this one is going to bend up. You will get something like this, right? Although my drawing is ugly, but it doesn't matter. Because the point is in your heart, you know what you are drawing. Now, this is something very, very confusing. Very, very confusing. So I would like you to memorize it if you cannot, because that's how I solve the problem. I always remember negative push up. Why? Because the band diagram is for electron. You put a negative potential, it means you increase the energy of the electron. So you go up. Okay, you agree or not, you understand or not, right? As long as you want to pass this class, just memorize it, right? You apply a negative bias, the side that you apply the negative bias go up. So if one side go up, the other side go down, right? In reality, how do I get this Venn diagram? I need to solve the Poisson equation. In reality, I know that when I apply a negative charge to the gate, does the gate get positive or negative charge? Sorry, when I apply a negative voltage to the gate, does the gate get positive or negative charge? Anyone? Apply a negative charge to the gate, right? Negative voltage, what does it mean? It means you try to push electron towards the gate, right? So is it negative or positive?
Negative.
Negative, thank you. Maybe it's too easy, you don't want to answer, right? So I have a delta charge here. And at the same time, the other side has to be positive because for charge balance, right? If you have a charge here, okay? So this is at negative condition. In negative, this must be electron, right? And what are these positive charge here? What are the positive charge in the substrate? What else can it be?
Holes.
Huh?
Holes.
Holes, thank you. You either have hole or electron, right? Or actually, you can also have other donor, etc. But this is the hole. Now you look back. The whole band diagram you can deduce by using the Poisson equation, right? We will try to do one exercise like this later. But now I just give you the result, the self-consistent result. Is this difficult? It should not be difficult because everything is just your intuition. This is just a capacitor. You apply a positive, negative voltage on the top of the capacitor. Of course, you get negative charge on top. You apply and then the other side will be positive. So nothing new, right? You know that already. Okay. Now, what if I apply a positive gate bias, right? But still smaller than the VTH? What will happen? How will it bend? Will you continue to, the metal side, will you continue to go up or go down? When I apply a positive bias.
Will it go down?
Sorry, say again, up or down the Fermi level? When I apply a positive bias.
The Fermi level of the metal will go down?
Will go down. Thank you. Right? We just say that you apply the process, push it down, right? Just memorize it. Sometimes for difficult thing, we need to choose to memorize it first. And when we are very good at that, we will suddenly understand everything. Really, okay? Instead of struggling to understanding it for many days, just take it as it is, trust me. And eventually you will suddenly get enlightened, right? So it will go down. It will go down, as I said, this is just the rock, right? I have 4 rock, right? 4 bar, right? How do you do, I don't know what you call this, right? And then you have this knob connecting them. Now you push this side down, then of course this is tilted, right? It's tilted, and then this side will be something like this. Okay? Now my question is, how about the charge? What is the charge on at the gate now in this region? Is it positive or negative? I apply a positive charge to it. Is it positive or negative?
Positive.
Positive. Thank you. Now, this is positive. It might not build to hole because it's metal, but still just a positive charge because it's lack of electron. Anyway, it's positive. How about at the bottom? It's supposed to be negative, right? But however, it is not a delta function. They don't all accumulate at the same place. You will see something like this. What is this? Can someone tell me? What do you call this? Let me go back. When Vg is smaller than 0, we have a lot of hole here. We say the hole accumulate at the surface, right? The hole accumulates, correct? Because the hole are all attracted to the top due to negative bias. And we have a lot of hole because this is P substrate. So they accumulate, okay? A lot of people of type A, they all accumulate here. Now we try to reduce I try to add a positive gate voltage, and this hole is going to repel away. So do you still have hole here? It will be less. So we say that this is a depletion. Thank you. Depletion. Depletion of hole. Depletion of carrier. Why is that? Because if you go back to the basics, we remember we have, for example, boron. We have these boron atoms. And then they come up with hole. They are negative charge. And then release a hole, right? Negative charge, release a hole. Overall is uncharged. Now the holes are gone. Then you only have negative charge boron. So these are the ionized acceptor. Okay. Are they mobile? Can they move? Can this ionized acceptor move? Can the boron move in your device?
No.
No, they are atoms. They cannot move. So we have charge, a lot of charge, but they cannot move. So they cannot contribute to any electric current. Okay? So what do? We keep increasing the Vg to be larger than Vth. Now, this is really low. A very big electric field here, right? And this is the Fermi level. I might not draw exaggerate enough, but the point is, here you see that the Fermi level go above the conduction band at the surface. Do you see that? Besides this depletion charge, this ionized acceptor, what else do we have? We have a lot of positive charge here. Here we also have some depletion charge, but at the same time we start accumulate electron. This is Na minus. Right? When your electric is so high, yes, you keep depleting, but eventually it is so high that the conduction band is below the Fermi level, and I have a lot of electron. And now, can this acceptor move still? This boron, can it move?
No.
No. So they still cannot contribute to current. But how about the electron? Can they move? They can, right? Now a channel is formed. And we call this inversion. Someone tell me why this is called inversion. This is called accumulation. Well, accumulates the hole. This is called depletion. Depletion of hole and electron. And this is called inversion. What does it mean?
So you start with the P-type, I guess, and then now since the Fermi level is above the conduction band. It's like n times, so inverted.
Excellent. Exactly. Right? Because we start with the p-type, now with a lot of hole, with high enough electric field, it becomes n-type at the top, right? N-type in the sense that it has more electron. So we say it is inverted, okay? Now I'm saying something maybe too trivial for you, but here I try to be slow because being able to play with this band diagram is very essential for you to be successful in this class and also in device physics. If you cannot, if you can explain things using the band diagram, you save a lot of physics and math. Okay, so I hope that you go home, understand everything, draw it yourself. Okay, but there is one thing. What do we mean by inversion, right? You can have a large inversion, or you can keep adding the positive charge to let it bend a lot, right? So we still need to give a definition of what is the meaning of VTH, okay? So now let's go back to here. Do you see this Q5B, which is the, sorry, let me, maybe it's better. Yeah, so my excuse for doing a very lousy slides is that I want you to redo so you understand what's going on. Of course, the real reason is my handwriting is bad, and also it's very difficult to write on the screen, right? But so when VG, right, equals to VTH, we call the threshold voltage. And how do we define it? We define it as this. First of all, you see that we have something called Q phi B, Q psi B, which is EI minus EF, right? This is the original EI and EF, and it determines how much hole you have, if you remember. We'll go to that later, right? If the EF is very close to the valence band, you have a lot of hole. So in order to make it invert, we basically, we want the surface to have the same amount of Q phi B, but for electron, okay? Right? Need surface potential to bend by 2Q phi B. Okay? Because when it is bended by 2Q phi B, then my electron concentration is the same as hole. And at this stage, the depletion width, WD mass, it will just stay there. WD mass is just due to the same equation we have been talking about. Maybe you forgot, but again, you know that is inversely proportional to Na, the doping, right? There's a 2, that's okay, you forget. It's proportional to the silicon charge. And then the potential is 2Q phi B. Do you see that? It's just saying that our surface is bended by that. Okay, here is VG larger than VTH, so I bend more than that, right? So if it is just 2Q phi B, then it is bending by this, so that this one bend down, the distance here equals to the distance here. Okay, any questions?
So WD is the width of the channel?
WD is the width of the depletion layer. We are looking vertically from the gate to the substrate, not the channel, right? So what we are cutting here is this. If this is the transistor, source, drain, and this is the gate, right? This is what we are cutting. We are cutting A dash. So this is A, this is A dash. Is that clear?
Yes, thanks.
Okay. Any questions?
I have a couple questions, Professor.
Yeah.
On the on the case where you put the gate voltage was greater than the threshold voltage, um, you said that it became an n-type material, but an n-type material becomes when the Fermi level is greater than the intrinsic energy, right?
Yeah.
You didn't draw that, right?
Intrinsic is just the middle of the conduction band and valence band, right? What is intrinsic?
Yeah, the EI, that's what I meant.
So it's just the middle between it. So this is the intrinsic. So you're right. So you see that at the bottom.
Oh, okay, I see it better now. I understand why it's inversion now. Okay.
Yeah. Good.
Okay, I got it. And another question is, we're using the doping Ni because we're working with a P substrate, right? In the case that we're working with an N-type semiconductor instead of a P-type, the same equations will hold, but we changed Ni to N sector N. What was the other donor? Ni and
ND. Sorry, this
ND?
this is NA.
Na.
Yeah. So yes, we change it to ND and become plus. So
Okay.
donor, yeah.
And everything else holds the same thought logic, the same accumulation, depletion, inversion, and the same equations?
Yes, everything is the same except that you have to be careful about the sign, whether it's positive or negative.
Okay.
Yeah. But all the logic are the same. Okay.
Got it.
Okay. Any more questions? So I urge you to go home to try the P-type, the N-type substrate means for PMOS. See if you can do that. Okay. Now this is the summary, right? So this is the summary of what I said. If you don't like my drawing, it is very clear here. Okay. So I'm not going to spend time on this here, but let's label, right? What is the first graph? Is it accumulation or inversion or depletion? The first one, this one. Top left.
Wait.
Accumulation.
Accumulation?
Accumulation.
Why? Because we accumulate a lot of hole here, right? The Fermi level is below the valence band, right? A lot of hole, positive charge. How about this one? Is this, let's go this first, top right. What is that? Depletion or inversion?
Depletion.
Depletion, right? Because the bending is not enough, so the Fermi level is still close to EI. We don't have hole and we don't have electron, right? And eventually the inversion is enough, right? The conduction band is very low and it becomes inversion. We have the maximum depletion width and then you would just start accumulating electrons. So the feeling of this MOSFET, the most important thing is that when we start attracting negative charge for MOS or positive charge for PMOS, we actually start depleting the carrier. We increase the depletion width, and this does not contribute to current. This is immobile. So you need to wait until the bending is enough to accumulate this electron, which is mobile, for current conduction. Okay, this is very important, a very important concept. Now then let's look at the threshold voltage. How do we calculate the threshold voltage? Right, so here is threshold voltage. What does it mean? Now, we can have a lot of different equations, but I think let's try to look at it, understand what is a MOSFET. It's nothing but just a capacitor. At threshold voltage, I just told you, at threshold voltage, we actually bend the oxide by this, right? So this is just a capacitor at threshold voltage. Is that right? So at this point, of course, I connect this to ground. This is VG, right? At this point, I say VG equals to VTH. And based on capacitor, I know how much charge I have, right? CQ equal to CV. This is just a capacitor, okay? First of all, what is C? C here is just Cox, which we have been talking about epsilon Si divided by Tox. We're talking about per unit area, right? This is the thickness of the oxide. 1 nanometer, 2 nanometer, 3 nanometer. And I make a mistake. Can someone tell me what mistake I make in the capacitor equation? It is not silicon, it is what? Silicon dioxide, right? Because our insulator is silicon dioxide. This is the permittivity that we have, right? So let's call it again, permittivity. We studied before when we talk about Poisson equation. They are all connected together, right? Permittivity of silicon dioxide, 3.9. If you want to memorize, right? Of course, you still have the vacuum one, right? 8.8, right? Times in farad per cm, okay? If 12, then it's farad per meter. So looks like I know how to find the threshold voltage, isn't that? It looks like, so is it correct that threshold voltage equals to Cox, right? Because it's C times V, right? Cox, sorry, let me do it again, right? So Q equal CV, so VTH, right, equal to Q over C, is it? And then what is Q? Q, isn't that Q is just the charge here, the depletion charge, correct? Which make it into the maximum, right? And just now I told you the depletion width is this one, right? This is depletion width. So basically it's just equal to the depletion width maximum times the charge density, QNA, right? If you try to work it out, it is just equal to 2Q epsilon Si 25B Na divided by Cox. Correct? So you see that maybe none of us have thought about this before because we didn't have time. The threshold voltage is just equal to the voltage during which I have this amount of charge, the full depletion charge on the other side, just divided by Cox. Is this correct? But actually, this is not completely correct. This is only talking about the potential across the oxide. When you have a potential across the oxide, Vox, you see there's a bending in the silicon also. You also have a potential across the silicon. But what is the potential when it is just equals to threshold voltage? By definition, we already say that it is when it bent by 2Q5B. Okay, so I do have 2,5B here. So what I'm saying is wrong, is the question mark is wrong. This one is actually VOX. threshold voltage actually equal to VOX plus 25B. So threshold voltage is just equal to 25B plus square root 2Q epsilon SI 25B NA divided by Cox. So this is what you have learned before. Now, do you need to memorize the equation? No. You even don't need to put in your cheat sheet, I believe, right? My purpose in this class is not to ask you to memorize this, but in this process, I hope you have the insights into the threshold voltage of the MOSFET. You can forget all the details, but you need to remind yourself, threshold voltage, first of all, MOSFET is just a capacitor. That's it. We apply a voltage and induce some charge on the other side. And how do we find the threshold voltage? Threshold voltage is at the point you just depleted the substrate. You still have not formed the inversion charge yet. You just depleted it, okay? You don't have this inversion charge yet. That is the threshold voltage. And by definition, the threshold voltage is just the gate voltage. So you want to find what is the voltage across this oxide. What is the voltage across the semiconductor? You add them together, voltage across oxide plus voltage across semiconductor. And now you use your physical insight. Oh, at threshold voltage, I define as the voltage across the semiconductor as 25B. It bent by that amount. That is inversion. That is just a definition. So one day, if you want to develop your model, you can change the definition. This is not universal. This is just a toy model, okay? And what's the voltage of oxide? Oh, that is as simple as just the Q equal to CV, just a capacitor. It's just that, oh, we need to find out what is the charge on the other side, right? This is a little bit complicated, but forget about it. You don't need to memorize. All you need to know is it is the charge when you bend it by 25B, okay? And you Google or whatever, derive yourself. Then you get this equation, right? So you don't need to memorize. But in all my exam is testing you if you understand this, right? If you don't understand this, then I change a little bit, then you will get it wrong. Okay, any questions here? Is that clear or confusion? I mean, this is important, right? I want you to be absolutely clear. Okay, if no more question. Now, the problem here is we have been saying that the phi m equal to phi s. So even at zero bias, there's no bending. Okay, what if they are not the same? Then let's think about a PN diode. Can you tell me what type of device is this? Is it N or P on the left? What is this? Left is N or P?
N.
N, thank you. Because the Fermi level is close to the, yes, close to the conduction band. And the P is right. When you bring it together, definitely they don't have the same work function, right? Think about this. This is the vacuum. So this is the work function of P, right? And this is the work function of N. What do we know? We know that if we bring them together at zero bias, you will have something like this, right? So you also need to understand to do this easily for you, right? On the left, far away, it is still N. On the right, it is still P. The band has to be continuous. So here we have a depletion region. Okay, so that's okay. Now, they are not flat band. How can I make this guy flat band? Just use what I told you. What bias should I use to make it flat band? We can apply a bias, right? Should I apply positive or negative to the left in order to make it flat band?
Negative.
Negative, so that I can shift the Fermi level up. This is almost impossible in reality because you are going to get a lot of, so I don't draw here because I don't want to go to quasi-Fermi level yet. But you need to apply very large bias and you actually will burn your diode. It won't happen. But the main point here is that if I apply a negative bias or I actually apply phi word function of n minus word function of p, right? Word function of n is small, right? Word function of p is large, right? So this is a negative bias. I apply this, then I can make it flat band. So this is the idea. So for threshold voltage, what I can do is I apply a bias so that it is flat band, and then I continue to use this equation. Okay, so if it is not flat band, for example, right, at zero bias, right, you might have word function, they are not the same, right? So let me call this 1, right? So for 1, because phi m minus phi s is not equal to 0, let's just use the same methodology here. Word function of n is not the same as word function of p, right? This is n, this is p. What do? We apply a bias which is word function of n minus word function of p, then they will be flat band. So the threshold voltage will becomes word function of m minus word function of p plus the original definition, which is 2 phi s plus, now I just call this Q depletion, okay, to save my time. Here, this is Q depletion, okay? Right, so you see that all I need to do is just to add this term. It just means that I make it flat band. After flat band, you just go through the old derivation that we have, right? So when they are not flat band, I need extra voltage to make it flat band. Okay, and usually we write it as phi ms plus phi 2 phi s plus q d over c. Is that okay? Any questions? Right. Besides that, we may also have something called interface charge. This interface charge may reside, this is the oxide, you might have the interface charge. They can be traps or they can fixed charge. Fixed charge means that they never change their nature. They are always plus, positive or negative. But interface trap, they can trap electron or they can detrap electron. We are going to cover it later in the next slide, right? But is that a difficult thing? No, because again, remember, this is just a capacitor. It's just saying that I need to support extra charge. Then in order to get into the 2 phi s condition, I just need to add additional voltage. So because of that, right, VTH will have to add another term, and you trust me, it's just negative Q interface trap or Q fixed charge divided by C ox. Again, Q divided by C is the extra voltage, right? And then we plus Q phi ms plus 2 phi s plus QD over C ox. Okay? And that's usually what we call this one as the flat band voltage. You apply this bias, whether you have charge or not, whether your Fermi word function are the same or not, you apply this flat band voltage, then the band is flat. And then we will try to invert it. So this is what you have been seeing in your textbook in the past. It is flat band voltage plus 2 phi s plus QD divided by C ox. Okay, so again, I don't ask you to memorize, but now I hope you have the insight the charge and the work function will bend my structure. So I need to make them flat band first, and then I derive the voltage. I need to invert the channel. So with this knowledge, if I give you something new, for example, some device called depletion mode, some called enhancement mode, some a junctionless device. By using the same knowledge, you will be able to derive what the VTH is. Okay. Now, very important is that look at this negative sign. It means that if I have a positive interface charge, would I have a lower or a higher threshold voltage? If I have a positive charge, lower. And do we need to memorize? No. Why? If I have positive charge here, you can think of that. Then it's going to attract more electron. I positive fixed charge here. Then I attract more electron. Then of course I can have the channel form earlier. So I have lower threshold voltage, right? That's how we try to memorize the equation through understanding. Then you won't mess up by using plus. Okay, if not, still just memorize with minus. Okay, any questions about the threshold voltage? If no, then I go to another topic, right? It's about the interface trap I just told you. So at the interface, there's something called trap. What is trap? Just think about in English, it's trap. You trap the animal, trap something. But here it traps the carrier. It can trapping the electron or trapping the hole. If it trap the electron cannot move. But it contributes to the charge. So as you can say, if I trap more electron, you need to increase the threshold voltage because you have less electron, right? So two types of acceptor, two types of state of traps. One is called acceptor, one is called donor. Okay, so how to memorize this? Just memorize it. What is acceptor? Acceptor is this. How about let's talk about donor first. Donor, right? You donate something, right? When you donate, it means that before you donate something, you are neutral, right? So if you are neutral, zero charge means charge equals to zero, right? If occupied by electron, means before you donate, right? Before you donate something, of course, that is your natural state, right? Before you donate something, so neutral. So tell me, after I donate the electron, what would it be? What type of state would it be? I was neutral before I donate an electron. Now I donate an electron. What type of state would I be? Positive or negative or neutral?
Positive.
Positive, right? Similarly, like acceptor. Acceptor, just think of a selfish guy, okay? You always just take away from people, okay? So before you take something from someone else, it's neutral, okay? Charge equals to zero if have nothing, right? A selfish guy, right? So this means before accepting an electron. Then what if it is occupied? What charge is it going to be? Is it positive, negative, or neutral?
Negative.
Negative, right? So what determines a state can be occupied or empty? What determines a state is occupied or empty in semiconductor physics? Look at this. Look at this. It's the Fermi level, whether your trap is above or below Fermi level, okay? If you are below the Fermi level, level, is it occupied or empty? When it is empty, it must be above. Fermi level. Okay? When it is occupied, it means it is below Fermi level. Same for donor. When it is occupied, this is occupied, okay? When it is below Fermi level. When it is empty, it is above Fermi level, right? So that is what I want you to understand. Like you cannot memorize, so confusing. Even writing cheat sheet is useless. The thing is you need to understand what is acceptor and donor state, and then when they can get occupied. It has to be below or above Fermi level, right? So on the right, each of these is a state. You can call it a defect state, interface state, right? So if whether the acceptor or donor is given by someone else, you don't know. I'm going to tell you. You came from experiment or came from an initial calculation, whatever, right? And then, for example, now I tell you this part is acceptor and this part is donor, okay? And you see that if the Fermi level is here, it is all negative for those level lower than Fermi level, right? Because they occupy. And if occupy, it is negative. And all those above are log charge. This is neutral. Similarly for donor, if it is below the Fermi level, they are neutral. If it is above, they lose the electron, they donate electron. So they are positive. Any questions? Any questions? Very important, right? We are going to keep reviewing, but I hope that at least you try to understand as much as possible at this moment. It's okay? Right? This is not difficult, but you need to follow the whole logic. Otherwise, it's so difficult to memorize. Okay? Now, good. So now we have everything, right? We learned the basics. Now, again, I say you don't need to memorize any equation. You need to understand the reason behind, because this is not a class just for MOSFET. You are going to apply this intuition to